My name is Dawid Zalewski, as you can see, and I'm going to talk about GDB. So I wouldn't say it's a niche topic, right? Uh, Everybody is debugging, and GDB is the most popular debugger, I think, in the world, at least when it comes to C, C++, and related languages that generate binaries. So let's do it. Welcome to the magic powers at your fingertips, which means that I'm going to be using lots of fingertips, my fingertips in particular. I have a couple of warnings before we start. So this is a high-risk talk. It's a high risk for you because you came here just after the lunch, which means that you have to, stay awake. I know it's difficult. I'm happy about it because I'm here, so I'm moving, right? I'm not going to fall asleep. It's also high-risk talk because I'm going to do a couple of live demos. Actually, it's mostly live demos, like half of it. And you know how it goes with live demos. It's dangerous. And what's even more dangerous is that most of the bugs that I'm going to debug live are generated by Copilot. So I was writing good programs and asking Copilot to spice it up with bugs. The issue is I might have not found all of them. So Copilot is very good at generating very bad code, as you might know. And so might be that I will get stuck on something, hopefully not. I'm kind of prepared. I have notes, so if you see me just looking here, I'm not texting with somebody, I'm looking at the notes. That's because I have to know what I'm talking about. I know what I'm talking about. I need to keep the order, and the order is kind of chaotic if I don't look up the notes. And that's pretty much all. So welcome again. We're going to talk about GDB, right? GDB is an acronym, and contrary to what the official logo might suggest, it's not a goldfish doing bubbles. It's a GNU debugger, which brings us to the core of today's talk. What is the debugger and what is the debugging, right? So just like everybody in this dire situation trying to find a good definition for something, I looked it up in the Oxford Dictionary. And it says it's the process of identifying and removing errors from computer hardware and software. I don't agree with it. This is absolutely not true. I've been programming for some years now, and this is what I'm doing all the time, basically. And I'm not always debugging. I almost do nothing else besides removing errors from software. So debugging must be something deeper. That must have a purpose to it. It's not just identifying and removing errors. So there's another definition. It's a bit more, I think, appropriate or reflects what's happening when you debug. And it says that it's an emergent activity. An emergent activity, for those of you who are not trained in psychology, just like I'm not, is something that happens when there are special circumstances when actually circumstances meet. And when they meet, there appears something that wasn't there before. Like, for example, when there is a heavy rain and the temperature is below 0 and there is a car going 100 miles per hour, an emergent activity might be an accident, which otherwise wouldn't have happened if those three factors didn't play a role. So that's an emergent activity. And it arises when the mental model of a program of its data differs from its observed runtime behavior. So we think we know something about the program, how it should work, but it doesn't work like this. And then we might start debugging, right? If you need to cite it, it's me. Let's look at a very simple example of what might debugging look like. We have an array of 3 integers inside. Some of you know what debug is. It's actually most of you know what debug is. It's a very simple bug. This program should return 42 because 1764 divided by the sum of 17 and 25 gives 42. It's basically 42 squared, 1764. But when you run it, when you compile it, and when you run it, and you print the result, it's not what you're going to get. You're going to get 49, right? So our mental model that basically 1764 divided by 42 should give 42 and also return 42 differs from the observed behavior. Now it's time to debug. That's how we debug most of the time. We want to make sure that both the compiler and the operating system did the right thing, and the value that the program returned was really printed to the screen. So we inject some print statement, just your normal printf debugging, and see what happens then. So after compiling, we are again at the same, basically, start. It's still 49 instead of 42. So that's not a good idea when you're debugging, right? Because you have to inject some statements and they leak into the runtime maybe, and into production. You don't really want it. You want to really fire up the debugger. So let's supplement this definition. It's an activity that arises when the mental model differs from the behavior and there is something extra. The underlying behavior or the reason cannot be easily found because we did printf and we couldn't find the reason. And only then we can talk about, I think, debugging. So let's start debugging. Since this talk is heavily based around GDB, I'm going to use mostly GCC or G++ as a compiler, but Clang works the same for it, and actually most of the compilers work the same. We compile the program and we fire up GDB. Of course in console, because that's how we try to debug. When you run it up, or when you start this program, you're going to be surprised, or maybe not. There will be no debug symbols found in the main. So we didn't manage to really properly compile. You see, when you compile for debugging, you generally do it differently than for production, right? And first and foremost, besides perhaps optimizing for debugging, you need to tell the compiler to emit the debug symbols. And switch both in GCC and Clang is -G for it. It emits debug symbols in the native format of the operating system. Or actually, not operating system, but the binary you are using. That's usually not good enough. -G has many other options you might not be aware of. And first, you might say that you are actually compiling for debugging with GDB. So it will emit symbols in the best format for GDB. And you might add a number to -G, like -G1, -G2, or -G3. The default is -G2, and -G3 is a bit better. It emits even more symbols, and specifically it allows you, for example, to debug macros, C macros, which are otherwise not possible to debug normally. So that's what you want. And just to be absolutely sure, nowadays you really want to do no omit frame pointer, no omit frame pointer. Omitting a frame pointer, which is basically a frame pointer, is simply using the base pointer register in your CPU to tell the program, or actually the debugger in this case, where the stack begins for the current function has been dropped when the systems were 32-bit. By default, compilers weren't emitting frame pointers, so weren't setting up the base pointer register. And that's because in those times, we didn't have a lot of registers in the CPU, so saving one was a lot. Nowadays, 64-bit architectures, there are lots of registers. You don't care about one simple base pointer register, just add it, so the debugger will know exactly where the stack starts for the current function. And you won't have any problems, at least not unless you're in the leaves, maybe. So let's do it. Let's compile for the proper thing, for the debugger, for the GDB, emit all the symbols, compile with almost no optimizations, OG, and run it. Run is the default, command you might do when you're GDBing. It runs the program. And if the program doesn't do anything special, it will just quit, which is very, unexciting, right? We don't want to just run the program, we want to debug it. So let's rewind and start again. Instead of doing run, you can start. Start does one more thing. It inserts a temporary breakpoint at the entry point of the program, which is exactly what you want. It will stop at the main. It will insert and directly start, and then we are in the main. Now, this is a lot of typing, right? Because GDB is a command line interface, but you get used to it. After you started, and GDB will display the next line to be executed, because this is basically like the next line that is going to be executed, number 4 with int main, you might press next. The next line is the standard array numbers definition, so the array definition. So again, we do next, or just press enter. If you press enter, the last command will be repeated automatically for you. Or you might also press N and enter, doesn't really matter. And then we're at the end of the program, right? Because the last statement in the program is the return statement, and we still haven't found the bug. So it's time to look at the data. You are always, I mean, in GDB, you can look at any data you want, private, non-private. You have access to pretty much everything. The most common thing to do is just to print it or p it. When you print it, you just name what you want to print and you see it. GDB works with pretty printers most of the time, so special scripts that basically tell GDB how to display information. And the standard libraries come with pretty printers. And if you don't install from sources, but just from your package managers, everything will be good and set up for you. Otherwise, you will have to tell GDB where the pretty printers are located. I'm not using pretty printers here. I'm just saying that I want to print directly the elements. So the array inside the array, the real array actually of the std array. And it will print something like this. And there is our first kind of discovery. It's a 13 and 23 inside, not 17 and 25, right? So that's not really what we wanted to have. Kind of surprising, because there should be something else there. Notice that GDB names the results. We have the $1, right? So every time you print something, you will get it back under a new name. $1 is something you can refer to. It's a variable created by the GDB, and from now on in this debugging session, $1 will always be this 3 elements array. Move forward, you can verify, for example, using the $1, if the 0th element and the first elements are 42. They are not, obviously. We can also check if the last element divided by 42 is 42. It is. And well, when you divide it by the sum of the first two, you're gonna get 49. So the compiler wasn't wrong. Our mental model of the program was wrong. And what truly was wrong is, well, we had octal numerals, right? Or octal literals in the array. So the numbers that we had weren't really integers, or there were integers, but not in base 10, they were in base 8. And they were, well, interpreted as such. So that was the mistake. Something you wouldn't find by debugging, but you know, it's a good thing to see it. Last command you might be interested in is list. That lets you see the program, but we'll talk about it in a moment. And that's pretty much the basics. So let's do it. Let's do it very quickly. I'm in the directory, in the build directory, and if you actually look at what's inside, this is my whole project. There are 6 different apps that I can build. The first one that I'm gonna do is actually the debug me one, which is exactly what we just saw a moment ago. Let's switch to build again. Almost. I'm already in the build. Let's fire the GDB, but before we do it, we have to make the program. Let's make it properly. So make clean first and then make. It builds with no warnings, and trust me, warnings are enabled. Still, all the programs are buggy. A great thing for debugging demo. And let's see how it goes. Let's do GDB. I have to go into the right directory. So debug me 01 and then GDB dbm 01. That's your typical GDB session, right? Doesn't show you a lot. I mean, it prints a lot of information and prints that it loaded symbols from the binary and nothing else. And we can start debugging. As I said, you can run the program, but that's quite yeah, not really good, at least not in this situation. Let's better start the program. So we start the program, and the temporary breakpoint was inserted, and you can see where you are in the program somewhere. Now that's unfortunate, but you can always display the 10 lines around your current execution point by pressing L and enter. And this will give you basically the beginning of the program. If I again press enter, I will see the next 10 lines, and then you can slowly start running. So you can do next. You can see what will be the next program line executed. This is this line. It's the next line to be executed. I still haven't executed it, which you can, by the way, see, because if I try to print numbers, I'm gonna go 0, 0, 0. So it's there, but it's nothing in there really. So let's do next. And now if I repeat print numbers, the elements are inside. I can refer to them, of course. So exactly what I did before, like print an element at index, I don't know, 1, which will give me 21, and so on and so on. And this is your basic debugging session, right? This is the absolute basics, something everybody should be aware of. And I think most of us are aware of the basics, like how to step through the program, how to actually next through the program, how to run the program, how to print something. Then come the more difficult things. So once you are running the program, you are not only restricted, of course, to one function, as I just was a moment ago. There might be multiple functions. Like in this case, there are 3 different functions, and you would like to visit also them. So let's do the same experiment as before. We start at main. We do the next, which will call the make Fibonacci, in this case, function. It's a function that makes a Fibonacci sequence, nothing really special. Returns a vector with a Fibonacci sequence of n numbers. And then we are at the next line. And here, instead of doing next, we are going to step. Next, when you press next, it executes the next line. In the current function, step executes the next line, wherever it is. That's the difference. So when you do step here, we are going to end up in the sum function that sums all the numbers in the Fibonacci sequence that's passed to it. When you're in a function, you have different choices. You can still go step or next, whatever you want. So you can basically explore the function. You can do, for example, next, and you will return from a function. Or you can just say that you are bored with the current function, because sometimes you are at the beginning of a very big function and you notice what happens already and you just want to return from it. The finish is a good command to go. Finishes the current function and steps out of it. And then there is a very fancy one, return. So you can influence the program's behavior. You can basically say that despite the fact that I'm at line 1 of the function sum, I already want to return from it and return 42. And it's going to work. This function will return, or actually GDB will return 42 for you. And this will result in the sum Fibonacci at the end, getting the number 42. As you have seen already, GDB is not really friendly when it comes to displaying source code, right? Because you have to press L. So some people prefer to use the text user interface, the TUI mode. And I'm going to use it sometimes just because then you see a bigger piece of code, you know what's going on. You can always switch in and out of it by pressing Ctrl X followed by A. It's quite okay actually to debug like this. Sometimes it gets stuck. Actually, it gets stuck every 3 seconds, roughly speaking. And for this, you need to refresh the screen pressing the Ctrl L. I think I press Ctrl L like a lot. And I'm going to do it also here. So let's do the second program. Let's go back from that one. Move to the next one on the list. It's 02. Make it, actually, I think I made everything. Yes, I made everything already. And GDB DBM 02. So we are in the next program, and this time I'm going to switch into the graphical mode. So not really graphical, but into the text interface mode. So this is my program, and I'm nowhere, right? I haven't started it yet, but it loaded the source associated with the program. Let's start it. We press, actually we don't press, we do start and see what happens. And now it's quite helpful. You can see exactly which line you are at and which line will be executed next when you press next. So let's do it. Let's do next here. Great. Let's do another next. So now the Fibonacci should be there. I can print the Fibonacci. It's a vector of length 11, capacity 16, and there are lots of things inside. You can see that there are numbers. They're properly populated. I can again do next, and now let's do continue. C is for continue. It basically goes further in the program. And it actually exited with code 01, which is a failure. And the unfortunate thing is that I have a small bug in the program. So let's run it again and try not really to fix the bug, but at least to prevent the program from emitting a failure code at the end of it. The issue with this one, it's not really a bug, right? It's just that I don't know how the Fibonacci sequence works. And I asked for the 10 first Fibonacci numbers, but what I got is the 11 first Fibonacci numbers, because the indices start with 0, and I construct the sequence as if they started with 0, but inclusive the upper boundary, which is not really correct here. So let's do it again. I'm not gonna really modify this one. I could actually step into it, right? And I could say, I could modify the behavior also of the program. I could modify the upper boundary, but we are not that far yet. So I'm just gonna return from it by typing in finish and accept the vector that I got. And let's step into the next one function, the one that accumulates. Now I know that it's going to return a bad result, right? Because it's going to accumulate the range, which is a bit too one too many. So let's fake it. I can navigate to what the program expects. It expects 88 as the result. You know, let's make the program happy and return 88. GDB doesn't like it. It likes it, but it wants to be sure that you are sure. Yes, we want to return it. And we return it hopefully, and then we can next. And you can now see actually that if you print the sum Fibonacci, it's 88. So it's not what really the function calculated. It was I told GDB to return. If I continue now, the process exited normally. Great. So it's not really fixing the bug, but we managed to do something special in a way. We modified the runtime behavior of a program, right? Let's move forward. This is the basics. And most of the people who studied computer science at one point or another know at least this. And most of the programmers know at least this. So stepping through the program, returning, continuing, right? Nexting, breaking maybe. I didn't really break. I always break at the beginning. But there is, the breakpoint that you can set. And we will see them a lot. Also, they are coming up. But that's something everybody knows about. Now, what will happen next is something that's already not known to everybody, or at least not to everybody I know about. Let's say that we have a program like this one. It's again a Fibonacci. That's the last Fibonacci program I'm going to show today. It's a more fancy one. It uses a Fibonacci generator, which uses a cache because it's, more optimal for some reasons maybe to use a cache, and it does a couple of things. So it generates a number, and when you generate a number, the cache, or actually the Fibonacci generator, is checking the cache for what's inside, returns this number if it's there. If not, it calculates it, puts it in the cache. So let's say we stopped here at the Fibonacci generate. At this moment, we are in the function main, and there is a concept known as a stack frame, right? There is a stack, there are frames on the stack. Each stack frame belongs to a specific function. We are at frame 0, because this is the only function that we are executing. And once we are there, we can press next, or step, sorry, in this case, and we are gonna step into the next function, into the generate function. Now we have two stack frames, and the innermost is the 0th frame, and the main frame became frame 1. Both of them have variables, local variables associated with them, and arguments that you pass to the function, including the implicit this argument if it's a member function. Let's step again, and again we are in a frame. Now the frame of the get cached becomes the 0th frame, and the rest is growing up, so 1 and 2. Now you can watch the frames. When you break in a program, you can see the frames. You can see the content of the frames every time you're in a program. And what's better, you can navigate through the frames. So every time you stop in the program, when you debug it, you can navigate through the frames. You can change things in the frames. You can do whatever you want pretty much. And there are commands for it. Like, for example, you can print the whole trace of the frames with the backtrace command. You can navigate through the frames with the frame, and you can go up and down with up and down. And we are going to do just this. So we are going to, I'm going to do backtrace frames up, down, and show you how this works. We should go, or I should go to debug me 3 because we are already at debug me 3. Let's do the GDB minus quiet and dbm 03, reading symbols, clear it. By the way, I don't have a specific slide on it, but sometimes you will see me, like in this case, doing an exclamation mark followed by something. This is calling a shell command. So I'm talking then directly to the shell, and I can execute something in the shell, like the clear, for example, to clear the console. I can also call make like this. Make actually is special. You don't need an exclamation mark. You can just make it directly. But you can pretty much do anything, like place the current directory, right? And it will show you what's inside. Let's clear again. We are in the program. Switch to the good mode. And first, let's do something like run the program. So let's run the program. It tells me, asks me for a Fibonacci number, negative number to quit. Now that looks interesting. Let's quit the program directly, see how it fares. And that's kind of, I wouldn't say disappointing, but the program just has crashed. Let's repeat the experiment. Enter -1, and you can see that there was a segfault, segmentation fault, which usually is caused by reading a null pointer somewhere. Now your program has crashed. What do you do then? You haven't finished running the program at this stage. That might be surprising, but if you're in the debugger, you haven't finished running the program. You are still in the program. It's actually a prime time to debug it. Now the first thing to do is, of course, see where it happens. And you can do it by basically saying frame or just F, and it will print you exactly where the bug happened. So this is where the program has crashed. It has crashed at the line return.value cache n. That's good. How did it happen? Now the backtrace comes in handy because this will, you can see the whole backtrace. This will print all the functions that were called one after another. And you can see what actually caused the crash to happen. So you can see that there is some main, and then we call the generate function, and then we are crashing. And that's quite surprising, right? Because the program told me that it's gonna quit if I enter a negative value, but it didn't. So somewhere, most likely in the 0th frame, so I'm gonna switch to the 0th frame, somewhere at this moment, when I print the n, it's gonna say that it's -1, and I tried to get something from the cache at index -1, which most likely wasn't the ideal situation. We can check what the cache is. So we can say, what is cache? If we are unsure, it tells me it's a vector of unsigned long. Great. I tried to access something from the vector at the index -1. That's not really a fortunate situation. Let's print the cache itself and see what it has. It has no capacity, no length. So most likely it means that I just dereference the null pointer somewhere, right? And then dereference it, yeah, like it's not even a null. It's, I don't know, null minus one, something like this. Not good. I shouldn't have done it. I have a bug, and that's very clear. And to really fix the bug, I guess I have to go to the editor and see how it happened, because this is the only situation, I mean, the only thing that I can most likely do. So I'm in the editor, and I promised somewhere that I will quit the program if the number is negative, but I'm not doing it, right? I read from state C in, and despite the number being non-negative, I just, yeah, don't do anything. So let's, with the help of Copilot, I kept it enabled because it knows what I want to do all the time. That's great. And I can type in faster. Let's do something very simple. If n is less than 0, break, and we are good to go. I mean, we should be good to go. Switch back to the debugger. Can I make it? Yes, I can make it from here. So it will remake it, and I can run it again. Run from the start, enter negative, it quit. Perfect, right? It's perfect. It works as expected. Is there anything else we can do? Yes, we can, because this program is not fixed. So we already have a segmentation fault, great, but this is not the end of the story. There are more things that will happen, and fortunately, we'll see them in a moment happening. So let's move back to this one. We already have the new program, and let's start it again. So I'm gonna do start, insert a temporary breakpoint. Oh no, just for the fun of it, let's do it manually. So let's run it again. Clear, because I always do start. And let's now not do start, let's do normal run, but insert the temporary breakpoint just like the GDB does for us. You do it with TB. TB stands for the temporary breakpoint. It's a breakpoint that's only going to be hit once and never again. So once it stops, you can continue. So TB at main, the temporary breakpoint was inserted. Now we can run instead of starting. Great, we are there. Do we need a breakpoint? No, let's just see how the program runs. So enter a Fibonacci number. If I enter -1, we know it won't work. It will work correctly. So let's do something crazy. Or let's not do anything crazy. Let's do 10. 10, 55. It happens to be correct. 55 is the 10th Fibonacci number in the sequence. So it works, at least for 10. Great. Let's try something else. 20 still works. 150. That's again something bad. Something bad happened, right? The program crashed again. I mean, that's the whole purpose of this demo. You will see lots of crashing programs. And now we could do the same as before. We could backtrace, right, and see where the crash happened. But for fun, let's do something else. GDB works pretty well with C++. As you have already seen, because I'm working with classes, it works so well that you can, for example, catch an exception. So there you can catch an exception when it's being thrown, or you can catch it when it's being called, whatever you want. I can see actually what a kind of exception was thrown, right? This is the std length error. So let's try to catch it. I'm gonna do catch throw. I mean, it looks stupid, but not as stupid as catch, which catches an exception that's being called and stops the program at the execution. Catch throw catches an exception when it's being thrown. So, and I'm gonna catch, and let's do it in the quotes, in the single quotes. Single quotes are your basically key to C++ and GDB, especially if you have namespaces, because GDB sometimes gets crazy when it sees namespaces and cannot resolve a name. So we need to stop at logic error. Let's do catch throw logic error. We just created a catch point. Great. A catchpoint is just a breakpoint. I mean, there are different names for breakpoints, but a catchpoint is just one of them. You can always display the current breakpoints, all of them, by doing info B. And now we have only one. The first one was this temporary that basically we had before. It was deleted already automatically. You can see it's a catchpoint. It has to match state logic error. You can actually see pretty much what kind of a description is there, like it happens when the exception is being thrown. It's enabled. We can always disable it if we want by doing this and 2. This will disable it. If we don't want it for some time, and then re-enable with enable, again with the number of the exception that we want to enable. It's there. And there are many different options you can do it. We can ignore it for some time. We can delete it, and so on, pretty much whatever you want. Anyway, we have a catch point. So let's run the program again. And I'm going to enter exactly the same sequence, just in case my program is deterministic. I think it is. So it crashed at 150. Oh, it didn't catch it. Did I do the catch point correctly? Yes, I was typing it correctly, but then that's good because we can delete it, right? So I just deleted it, and then do length. I don't know why I did logic, but thank you for this. That's must be this one. So let's run again. Yes, 10, 20, 150, and it still didn't work. And actually, this time I know why it didn't work. So that's one of these very weird times when GDB doesn't like the single quotes. Normally, whenever you work with symbols, C++ symbols, you have to work single quotes. This is the only time you don't. And don't ask me why. So let's run it again and just do it very quickly to 150. And now it worked. So now it matched the symbol and we stopped at catch point 4, exception being thrown. Now, backtrace. You need the backtrace always. And there are lots of things happening. Now, there are frames, right? So let's go from the first one that looks like something that I can understand, which is frame number 2. So let's go to frame number 2. Info args, those are the arguments passed to this function. Can you see something strange? I mean, there is a huge number there, right? A horribly huge number. And this is a call to reserve, if I am not mistaken. So if you look at the source code, we are at the vector reserve and the n, so let's print the n, is a huge number. That's not good, right? That's why we got the exception length error, most likely. You can always print it with args if you don't want to, if you want to just get all the arguments together. I think there are no locals here, but you could also print the local variables if there were any. There are no locals, so there is nothing there. Or you can just do f frame, which will basically print everything that's in the current frame. A simpler way of doing things. So something went wrong. Let's go up, up, up to cache reserve. So there is this call to the cache reserve somewhere. So I'm reserving the cache. I'm basically telling the vector to grow. And if you print the n this time, so let's print the n, you're going to see it's minus 106. So that's not exactly what I was passing, right? Because if you go one frame up to the calling function, you're going to see that the n was 150. So there is a mismatch. And by observing it very slowly, so let's go down a frame, and scrolling through the source, you, I think, going to see very quickly the source of the error. We are getting a car here, a signed character, hopefully. The problem is it's only 8 bits, but I'm passing an integer to it. So there is some bad things happening. I'm passing 150, an int, it overflows and goes to a negative number. So a fix is, of course, to fix this number, right? So we shouldn't get a car here. There should be an int or something respectable. Most likely, we should also insert some checks for it, which I'm not doing, but let it be like this. Let's not, go any further than this. Quit it, make, so the target has been built, run again from GDB, and let's do the puzzle again. This works. 150 at least gets accepted, doesn't crash the program anymore, good, right? And if I enter something negative like -1, it quits as it should. Now this is not the end of it. This program is actually still buggy, but I decided to leave it like this because the other bugs are not so interesting. So we'll move forward to the next bugs. Again, sorry, I didn't hear you. No, that's a good question. No, micro is a text editor, and I'm calling basically a script under the hood then that fires up micro with the current line of code in the current frame. So, but you can set it up for any editor you want. I just set it up for this one because I don't have to switch constantly. We can talk about it later on. So we're here, right? Debug me 03 went found. We even made some small breakpoints. And there are lots of things that can be done with the breakpoint, like you can set a breakpoint, right? I'm not really going to talk a lot about it. It's just one slide about it. We've seen that you can delete a breakpoint. We did it. Or we did it with a catchpoint, but it's the same. Enable, disable, we did it. Didn't really use it, but it's there. You can also ignore a breakpoint for some number of executions if you want. Set breakpoints conditionally, which is super cool, and we're going to do it at the end of the talk. Auto remove conditions, which we are also going to do. Display the breakpoints, which we did. And last but not least, save the breakpoints to a file, which is a super good thing, right? You save all the breakpoints, and it remembers it, and then you can load them. I'm not going to do it because I don't really need it. I never step out of the GDB. I recompile it within using make, so my breakpoints are saved. They persist, but otherwise, if you need to quit GDB, remember you can save the breakpoints. Next, we are going to talk about the real stuff, about money. So for the remainder of this talk, I'm going to use one example, a money pot. It's a pot with money. And it's a class called money pot. It has a goal, which can be like a trip to the moon. People are saving for the trip to the moon or whatever. It's a group of friends. There's a target, so whatever they want to save. There are deposits, so everybody can, put money into it. There is some size of deposits, so how many are there already in the money pot? There is a capacity which hints actually at manual memory management, because there is a capacity of how many deposits I can hold, and there is a size. And you're not wrong, because the deposits is a dynamic array. I needed a dynamic array because that's really good, easy to make errors with it and bugs. And there are some functions like total, which displays, gives you the amount of money already stored in the pot. Add deposit, which adds a single deposit into it. You can check if somebody's contributor to it, and check how much money somebody put into the pot. And there is also a deposit. It's a simple struct, a pot, which just has the name and an amount. And the idea is that, there's a group of friends, they put money, everybody I put $10 one time, another time 20, so I have two deposits for 10 and 20, together 30, and I can list them, and we know how much we saved for our target, whatever it is. And I'm going to use it a lot in this presentation, in the reminder of the presentation, and we are going to start with a core dump. This is the only AI-generated image I have, and I really had trouble with it. So DALL-E refused to generate a computer experiencing a core dump. It was telling me that it's offensive, so literally. So I think that it gains consciousness, I'm afraid. So we have to be aware of it. I finally managed, and that's one. Notice the nice calm background and a computer in panic. So only this made it through the filters that are there, profanity filters, whatever they are. We are going to do a core dump. That's a fun thing to do, always. So let's quit it. Let's cd to the dbm, debug. Debug me 4. It's already made, and I can do dbm04. When I run it, basically you can see that there is some pod being happening there, a bit buggy because the goal doesn't display properly, but there is a total remaining 1400 deposits, which are none here, and the core has been dumped, which is a lie. There is no core that has been dumped, right? So it says so, but depending on the system that you're running it on, most of the time there is no core dumped unless you set a limit for the core dumps to something bigger than 0. And by default, it sets to 0. So this is the limit for the core dumps. You can set it to unlimited. So let's set it to unlimited. And now if I run the program, so let's run it again, the core has been truly dumped. I'm on Ubuntu, so my cores are in a very specific location, and I can actually pick it up. It's in the var. You can look it up for your system, whatever the system is. Took me some time to find it, but it might happen. And you can see there are pretty much a lot of core dumps there. Let's remove them for now. So let's remove everything that I have there and core dump again. So not rf, rm I wanted to do, right? Remove. And I need sudo because apparently, because I don't know which one generated this one. So I really want to remove them. Yes, removed. And let's generate another core dump very quickly. And now it's the only one there. Great. Let's copy it. Let's copy it to my current directory. And then this is the name of this core dump, and let's just call it core. Yes, the names are quite horrific, so I don't want to work with them. I just copied this core into my directory, so I have it directly at hand. And now you can debug a core. So a core is just a dump of raw memory of a program, right? Something that happens very often. I mean, not very often, but you might set up your system to dump cores on the customer side. Useful for debugging. So let's debug it. GDB. And my program is still dbm04. And I'm going to add core to it. So you can just directly load core. You can also load the core later on if you want. I just want it directly. Here it is. So I loaded the core, and I can directly see that I segfaulted. Right? I have a segmentation fault. Not a good thing to happen. What do you do then? Well, the standard thing. Backtrace. It's a segmentation fault, so the backtrace is your friend. It will point you directly to the error. And in this case, you already can see the error happening somewhere. You can see it here, right? There is some class pod deposit, and the function is being called name. And this is 0, 0, which is not good. Let's switch to frame number 2. See what's there. It's a very simple function. Let's see what arguments were passed to it. And you can see that there is this, 0, 0. Not good. Let's go up the frame. And here we are. This is basically from here we crashed. So we were passing some deposit. Basically this one, I think this is the offending line, deposit arrow name, that tried to a function that, I mean, we're comparing two names, and that's how it went. So apparently our deposit is null. Verify it. Now info locals will work. You can see that deposit is indeed null. So we received a null deposit from find deposit. Now that's not that great. Let's see what find deposit looks like. This is my find deposit, and I think I hit the last line, which returns a null pointer under some conditions, right? So basically, if you look at this, let's switch to the second frame again, or maybe let's go one up and do the micro again. The problem is I'm not checking for the null pointer somewhere, and that's why I crashed. So let's return or not return. Let's do something like if not deposit, then directly return. Great. Save, quit, make. That didn't work very well. Yes, I have to return a bool. And now I cannot micro again because I cannot debug, which is very unfortunate. But I always have like the second choice here. Thank you for it. People, I mean, the audience is usually more observant than I am. That's good. So we were crashing. Oh, here. I have to return something. Yes, false. Now it's happy. So let's go here again. Make. Now I can run it, and it works, right? It kind of works very well. So, I mean, it doesn't crash. It works in the sense it doesn't crash. It doesn't mean that it's correct. So now we really had a core dump. We really debugged it, and you saw how it's done. Now, what follows is a bit of printing, because debugging is usually lots of printing. And GDB supports different ways of printing. So we are going to print a lot. There are different ways of printing. You've seen already print, which basically just prints something. You've seen you've only seen print, but there are many, or at least 2 other ways of printing. There's a display, which is automatic display, a very handy one because it displays variables you tell it or objects you tell it to print at each step. And there is a debug print, which is amazing because it allows you to do printf debugging in GDB by kind of automatically. So let's just do those. I run the program, right? And if you look at it, it doesn't really work correctly, or there is something fishy going on. And most likely, or first, not most likely, but I'm telling it because it says that the total of all my deposits is 100, but if you sum it up manually, it's not really 100. So there is like 30, 55, around 70 here, not 100. So there is something going on there which is not correct. Now let's break at total of. Now I don't have to qualify the name. I can just do the total of, and GDB will put a breakpoint at everything that matches total of. For me, it's a function. No, I need to start it. It's total, sorry, it's just a total. So break at total. It prints the total, so let's break it and let's run it and see what's going on there. Again, the nice mode, it sums everything, so it seems that it's correct. I call it only once. I can see what arguments have been passed to it. It also looks correct. I can print this. And you can see that this is a proper object. It has a goal, trip to the moon with some target and the deposit size. Everything is correct. And there is deposits. So what is deposits? It's a row pointer. Great. Now you would like to see what's inside, right? It's a row pointer, but it's an array with the size of 12. At least that's what my object is telling me. I mean, you can always dereference the pointer. That's not a problem. So let's do dereference the pointer. But that will only kind of print you, or sorry, not what is. I wanted to do the backward. I wanted to print it. So let's print deposits, but it will only print the first one. And I want to see all 12. I can already see there is something fishy going on because it says there are 12 deposits, but the first one is wrong. Now let's go further. So let's do the printing of the whole array. Info locals, info args, and first and foremost, let's print this. There is a special syntax which will allow you to print more than one if it's an array in GDB. And the syntax is pretty easy. You just say how many elements you want to print. Like in this case, I want to print 12 elements, so I do add 12, and it will basically make an array out of it, and it will print all 12 of them. You can also use a variable for it. So if I wanted to do something like deposits size here, almost. That would be also okay. So I can just do it. Basically any arithmetics, any way I want. And you can see that there is something wrong there, right? It's totally wrong because it doesn't match, right? I mean, at least there shouldn't be 0 or nothing in the first place. Now, if you look at the main, there is this add sum function, which basically adds deposits to my simple pod by calling the add deposit function. So let's look at the add deposit. What it does, because apparently it does something wrong. Simple check, like rudimentary check of whether I need to increase the size of the array or not, but I don't really want to debug it. I want to kind of go back to the printf thing, because I'm pretty sure if I do it correctly, I will be able to catch the errors. Let's try to do it. And believe me or not, GDB supports printf debugging. So imagine you have this kind of a function like that one, add deposit, whatever it is, and you would like to insert printf statements in it. Now, you are not going to do it in the program. You can do it in the GDB. So imagine you wanted to print something in the beginning. Automatically, each time this function is called, well, you can do it. There is a function for it. It's called dprintf, debug printf. And you tell GDB where you want to inject it. Like, I want to inject it at the beginning of add deposit, and I want to print something. Great. It will inject it, and you will see it works great. There is even more to it. I can print like the whole array even. There is a special formatting sequence, %v, which will allow me to print objects, the whole objects, in the same way that print interprets them. Let's do it. Let's do it very quickly. I'm going to do it dprintf, and I want to do it at add deposit. And I want to print something like size is %d, and depths are %v, new line. And I want to do it like maybe before, right? So that's what happens before. I need to, of course, it's a normal printf, so you need to still do a lot of typing, unfortunately, and followed by this one. It's only one-time typing, luckily. And let's do, let's just print the first 5. I hope there are no typos, because if there are any typos, I'm gonna have problems in a moment. I think there were no typos. It works like a breakpoint. So you can list it as a breakpoint, and it's gonna show us a breakpoint. And you can see it there. And I want to inject another one at the end of add deposits. So let's list it. It's a line 86. So let's do one at line 86. So pod cpp at line 86. I want to see the after. So what happens after the call was made. 2 dprintfs added, and hopefully if I run it now, there are lots of things going to be happening. So you can see that every time the deposit was added, every time this function was called, the printf statement was injected into it, I got a full printout. And I can see indeed that deposits are not being added correctly. I mean, this is not what I'm adding. If you look at the source code, it shouldn't happen really. The size is correctly incremented, but the deposit, the first one, is put at the wrong place. Not that great, right? Let's break at add deposit, because this is the easiest way for me to basically, edit the code if needed. The bug is pretty obvious. I'm pre-decrementing instead of post-decrementing something, and that's the only thing that was wrong. Make info breakpoints, delete 3 and 4. Let's delete 3 and 4. And we kind of, made debug printing. Another kind of debug printing you might be interested in, and I'm going to do it in the total for function. It's a special function that calculates how much money everybody stored. Let's start it very quickly, and you will see how it works. Continue, and I'm in the total for function. And another one that you might be interested in, because this function is obviously also buggy, is something that prints automatically everything you want to print at each step. So let's step quickly through the function. For now, it's going okay. And let's now print 2 things. Let's print the name. It's Alice small letters, and let's print the deposit underscore I at name, which is a capital letter Alice. The comparison should work, but as you will notice, it doesn't. So it kind of doesn't, and you might want to verify what's going on. And for this one, there is an automatic display. You do it with disp. So we want to display always the name, and we always want to display the deposits at I.name. And let's next through it, and you can basically see at each step what happens. The GDB, every time at each steps, emits what the variables are. Something that might be handy when you are going through lots of data. Again, we have an example where the Alice name is small letter and the deposit's name is capital letters. Well, let's verify whether it works. Another magic power of GDB, you can call everything you want, right? So we can, for example, do call and code it to lower function. And let's call it first on the name, which is already the toLower, so that should work. It works. I mean, you are allowed to call everything when you're in a program. Let's call the other one. So let's call toLower. And I'm going to do 2 different things. First, I'm going to do the good thing. So let's step out of it. So let's call toLower deposits underscore I and name. I'm calling a function here. And you can see that it didn't toLower it, so it's still uppercase. And I'm going to do a bad thing. So something you have to be aware of when you use the built-in functionality of GDB to call functions that are part of your program. This won't work. It causes a terminate, an exception, and you might be surprised, because if you look directly at what actually, if I list the, I think it was deposit, of course it doesn't exist because it's in the namespace. No, that's very bad, right? Let's just list the whole deposit. I think it's called like this. I'm not doing well today, right? With this one at least. I hope it was called deposit then age. No, I don't know how it was called. Maybe big letters, doesn't matter. Now, anyways, no, I know how to do it. I know how to do it. I know how to do it. Let's run it. Yes, I want to start from the beginning because I am in the breakpoint. If you look at what it is, if you look at what is deposits at i.name, you're going to see next, or you're going to see in a moment. Where am I? This is the moment when I'm confused. It's going to rewind in a moment. So I'm going to continue, control, next, 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 next. Thank you. I am in a good context now. So if you look at what is deposits name, it returns you a standard string view. If you look at what to-lower accepts, it's also a string view. The name itself, on the other hand, is a standard string. And you can do it. The problem is, I mean, we tried to do it, right? We tried to do something like to-lower and then do deposits i.name, but it didn't work. Whereas the other one did work. Now it cannot, oh, it can, but I need to call, right? Whereas the other one did work. The reason is there are no runtime conversions happening. It's impossible, right? Those are functions that are already compiled. All the conversions that could have happened already happened at the compilation time. So there is no runtime conversion from a standard string to the standard string view. It's impossible. That happens at the compile time. So when I try to pass a standard string to it, it will basically just crash. Don't try to do it. This creates a lot of fancy problems, like it's diabolically difficult to, for example, create an object in the GDB if you want to test it with some functions. It's possible, but it involves malloc, calling constructors on the pointer, and so on and so on. So it's quite involved. Anyways, we identified, I think, the bug. The bug is in the to-lower function, and with that, we can move forward. So let's go back to the presentation. So we've done this one, we've done this one, and I'm going to now go directly to the slide 52, which is a planned thing. We are going to talk about a thing that's also kind of an ability of GDB, but before we do it, and it's a very good thing, but before we do it, we are going to deal with one more fancy bug. So let's go to the debug me 05 and try to run it directly. So run it, and this is dbm. Oh, not like this, of course, no space here. And basically it directly crashes. There is a logic error, core has been dumped, and so on and so on. Now, if you try to debug it, so GDB dbm 05, and basically start it. So I'm gonna start it. Let's go into this fancy mode. You can kind of very quickly see what's going on. I'm gonna step through it. So I'm gonna step into the next file. There is a from file, so I'm now reading some data from file, which I hopefully passed. Let's step, let's fin, step, finish. That's a lot of, I think I am now good. I mean, it wasn't that easy to find it. But the problem is, if I backtrace now, there is, let's run and backtrace. So the problem is, if you backtrace it correctly, is that there is some basic string construction happening, and it's being constructed from a null pointer. And if you look at the last frame, at the main frame, I can just directly switch to the F9 and see where it happens. It's exactly at this line. And as you can imagine, the construction from the null pointer happens because I'm constructing somewhere a standard string from argv1. You can always print arguments that has been passed to it. It's kind of uninformative because it's an array. So let's do it with an asterisk. Info that didn't work as expected. I wanted to do print, sorry, argv. And it will tell you basically, again, only one element, that's the name of my program. Let's print some more, like at 10, for example. And what you will see is, of course, that this is an empty array, or at least the element at index 1, which is here, somewhere lost, is null, because I haven't been passing any arguments to my program, right? So it's quite easy to do it when I run from here. I can just do dbm and pass like a file name. Let's do, I don't know, file.txt, but how do you do with GDB? There are different ways. You can, for example, call the GDB itself with the args and pass the argument to it, just like this. And now the argument will be passed. You can show it always. It will tell you that the list of arguments that are going to be passed is file.txt. Great. But you can also modify it later. So I can do, for example, start or run and pass like file.in. And if I run it now and try to print argv at 2, the file in has been passed, which is great. So I'm now passing something. I should have been passing it, but I wasn't. Let's skip the check for now. I mean, let's not skip the check. Let's just fix it because it's a ready to do check. So if stood, I should do it actually before, right? So I should do it here somewhere. And let's do if stood file system exists argv at 1 is good. Now let's not do it that complicated. Let's do just if argc is different than 2, then you simply return or maybe print something to the standard error stream, whatever it is, and you return 1. And argc has to be taken, of course, because I wasn't taking it. And now it's kind of good. I'm at least checking it, right? So I can quit. I can make it. It's going to build, luckily. And now if I try to run it, so let's do set args, which sets the arguments to the program, and run it. It's going to crash. I think so. I mean, it's not going to crash. It exits with code 1, but that's exactly what I wanted, right? So let's start with the file, and let's do something like that one. Start info.txt and continue. And again, it crashed. And now we're going to do something different. So instead of what we've done previously, examining the backtrace and so on, I'm going to do something that a lot of people like, which is the time travel debugging. The GDB supports it out of the box. So if you're running GDB, you can do time travel debugging, no problems whatsoever. However, it comes with some caveats. So let's quickly go through it. The normal order of things, of doing things when, this is what we've done, the normal order of doing things when you're doing time travel debugging is basically something like this. I mean, instead of executing the program from the beginning to the end, you execute it in any arbitrary direction. So you can either step or next through the program, or reverse step, reverse next through the program. And that's available out of the box when you're using GDB. That's no questions asked. It's good because you can always replay the program. So if you didn't catch something, you can always go back, see what's going on, step again, go back, whatever you want. And the normal order of how this should be done, imagine you have an app that crashes at some function, you set a breakpoint there, you know it's going to crash soon, so there is something going on. Recording is expensive, so you only want to do it for things that crash. You run it, you basically stop at the breakpoint and you start recording, right? Once your app has crashed after the continuing, you can reverse. So you can go back in time and examine everything step by step as much as you like. So let's try do it. I know it crashes, and I actually know it crashes quite quickly, right? So I don't even need to set a breakpoint. I will just clear it. Let's see if args are being passed. They are being passed. Great. So let's start the program from the beginning and let's record. Recording has started. Continue. And there is this thing happening, right? Basically, it tells me that the recording didn't happen. That's because, unfortunately, as of now, and this is the newest version of GDB, the recording functionality of GDB doesn't support the newest instructions, especially it doesn't support almost any vector instructions. And I'm using strings heavily, and strings are vectorized nowadays in all the standard library implementations, so it cannot record them properly. Now, there are two solutions to the problem. One is to use a special build of GDB called reverse GDB. Kidding, it's not a special build. It's a function that I have defined in my initialization script, which basically disables all the vectorization in the standard library. You can do it. So there are some environmental variables you can set up, right? There are lots of them. Disables all of them, including the SSE extensions, which are quite old, just to be absolutely sure. And I just yesterday found out that there are some extensions that are not disabled by it. But you can do it, right? You can disable all of them and run GDB, and it's gonna work. So let's do the reverse GDB, and then dbm 05 info. Great. I can start again and record, and hopefully it works. If not, there is another solution. And continuing. Did I pass anything? Yes, I need to stop the program because it should have crashed. So let's show the arguments. No, I didn't. So let's start again. Let's start, and now with info, because that's what it was crashing, right? So info, start, again, rinse and repeat, record, continue, and it managed to record. So there is a segmentation fault, and I recorded the trace. And now great things will happen because, and I will switch for a moment to this mode. I crashed in some function. I can go back in time, right? I can do reverse next. There are commands like reverse next, which with a shortcut rn, there's the reverse step, reverse continue, and there is a reverse finish. And the reverse finish is the most unfortunate one because somebody didn't alias it yet. So you have to type in at least reverse -f. For now on, let's do actually the reverse finish first. We are in some function. Let's do it again. Reverse finished, and now we are actually in the place where we should be, in the put function. Info arguments. This is null. So this is null. We again have a null pointer. We are in a member function. This shouldn't be null, not at this point, right? I can reproduce, by the way, the crash if I wanted. If I now press continue, it will again crash, which is pretty cool, but I don't want to do it. I want to go back. I want to see why it's null. So I'm going to do reverse step. Reverse step. There is going to be quite a lot of reverse steps. I think this is reverse next if I remember correctly, and now I have to really switch to reverse stepping. Again, reverse step. This requires some practice because the funny thing is that the function that you see highlighted is not the function that it's the function that already executed in the current context. So when you reverse, you are going to step into it, which is kind of mind-boggling. So you have to, in a way, understand what you're doing. And I think I don't now. Oh, I do. I am at some function that basically in the pod manager. So let's print, because I'm kind of in a pod manager, what is instance? Let's print the instance. It's a pot manager, and the pot inside, so my money pot is 0. Not good. Let's reverse step again, and now I'm back into the pot. I can see I am at the function that actually loads the file, or almost there. Reverse step one more time, and now if I go again, reverse step, I think we found the problem. So I'm opening a file stream, but as you can see, if I do rs now, or sorry, step now, I am directly going to the false, which means that the file wasn't open. However, my pot, which is somewhere here, is still being null, so it's not being initialized correctly in the case that I didn't manage to read from a file. So that's the basics of how you can reverse step and how you can use the GNU debugger for it. If you don't want to use the GNU debugger for it, there is another way. So I am back at this one. Mozilla has a great project, which is RR. It's for recording, right? It's much easier to do it because instead of what I was doing, I can just do RR record without setting any environmental variables and so on. dbm 05 and let's say info.text. It tells me now that which is actually something that happens all the time when I'm using it. I never want to set it permanently. So my performance counters don't allow recording of some events. Let's set it correctly. Sys control and lower the safety a little for the performance counter so RR can record properly. And now I should be able to record. That was it, I think. Right, segmentation fault, great. RR replay. And finally, it loaded. I'm back in my program. So I recorded the full trace, and I am basically executing it in the GNU debugger, but under a different alias of RR. I have to break at main because if you print the backtrace now, I am in some library functions which are not correctly decoded even because I am deep in whatever Mozilla came up with. So let's break at main, and you have to do it manually, I'm afraid. I'm already running, so I can continue. And hopefully it will stop at one point or another. It stopped. I am main, and I can now continue debugging, but doing it in either direction. So I can go next, for example, next, and step into it, or I can just reverse next, whatever I want, right? So we are both ways. You can go how much you want and wherever you want. Let's switch back to the presentation. So we've done this one, right? And it's pretty cool, reverse time debugging, and especially reverse time debugging with the RR is a piece of cake. So if you ever want to do it, use RR instead of the built-in GNU debugger recording facilities, because the pleasure is, the experience is much more pleasurable. And we kind of are at the end of this talk because I can see only 7 minutes left. So it's not a debugging story, right? We started doing slowly the things that are kind of in the territory between the intermediate and advanced. There is much more, and the more is mostly scripting of GDB. GDB nowadays can check your email if you want, just like any piece of software that evolves long enough. It's just enough to write a small Python script for it. So that was one of the questions, is micro built in? No, it's scripted. I actually scripted a lot of other things to hide some information from you that would help debugging, because I wanted to disable some messages that GDB would otherwise print. The next step would be, I think, investigating commands. So issuing automatic commands whenever you stop at a breakpoint or a watch point or whatever. You can tell debugger, your debugger to do something then. And then the next step is really writing your own function and extensions for GDB, which is pretty powerful, right? Because you can write your pretty printers, for example, for your own objects. You can write your own debugging functions, logging, whatever you want. But for now, that's the end. Thanks for listening and hanging around with me with the demo. It wasn't so many hiccups as I expected, so I don't know why. So thanks again, and that's all.